All right.
Welcome, everyone. We are looking forward to the next presentation by Tamar Avineri from the North Carolina School of Science and Mathematics, learning about modeling pollution levels in the Great Lakes.
Thank you so much, Tova. Thank you for coming to the session. I'm Tamar Avineri, and I'm a math instructor and department chair at the North Carolina School of Science and Math here in Durham, North Carolina. We're a residential public high school serving juniors and seniors. And we work hard to incorporate modeling into all of our classes. And the problem we're discussing today is a great example of that. So I'm looking forward to spending the next 30 minutes with you. I always like to present my talks in a way that models what happens in the classroom. So this will be an interactive session where I ask you some questions to work on as we move through the presentation. So if you need paper and something to write with, that might be good to have nearby. The problem that we'll be discussing is what we call our Great Lakes problem, and it's well placed into any single or multivariable calculus class or differential equations course. It involves a couple differential equations and the technique of integrating factors when solving analytically, but it's very accessible. I've done this in both a differential equations class and a single variable calculus class, and it's very accessible. So, there we go. In my classroom, I split students up into groups of 2 to 3, and they collaboratively work together to a final write-up that they turn in together. This typically takes about 2 to 3 days in the classroom, with their only homework outside of the classroom is to work on this. I don't give it in addition to. I'll give you a moment to read the problem prompt and give me a signal when you're ready. All right. So if we were to write differential equations to model this scenario, where would you start? We recognize that we need a system. And how many equations do we want to set up?
We're gonna need one from Huron to Erie, Erie to Ontario, and out of Ontario.
Nice. Yeah, so at least for sure 3. Yeah, and then we identify our labels. We set the stage with identifying what letters will represent what. Okay, can someone take a stab at Huron? And you could talk it out or put it in the chat. So the change in pollution level in Lake Huron every year.
So I guess we're assuming that it's well mixed.
Yes, exactly.
Yeah, okay.
Yes, right. Yes, and I wonder. I think that yes. So the very last sentence says the pollutant dissolves uniformly.
Oh, sorry, I should have. Yeah, the reading comprehension thing. Sorry.
No, there's a lot of info there, but yeah, exactly. Good assumption. If that wasn't there, that would be something I would want my students to make an assumption about. Yeah.
Yeah.
Absolutely. So if we think dH/dt, how is it changing? So we're looking at differential equation, not what's in there right now, is how it's changing. So where would we begin?
So I'm thinking like 3,500 plus 25 times the year, and then we're losing 11% of that every year. Or maybe I'm missing. It's been a while since I've done these.
Yeah. No, this is a really, really good start. We know that initially there's 3,500 in there, but we're modeling the change in pollution levels. So we wouldn't want to have the 3,500 incorporated.
Oh yeah, we don't need that.
Yep.
Yeah.
But we are gaining 25 every year, flat.
Yeah.
And doing it, what else?
Well, we lose 11% of the pollution floating around in there, right?
Exactly. So how would I incorporate that in my equation? We're losing 11% of what's in there.
Yeah.
So we could subtract 11% of the current H of T.
Absolutely. Yes. We have 25 fixed amount. Yep. Yep, Paul, exactly. I think you're just direct messaging me, so I'm not sure everyone can see it, but yes, DHDT is 25 minus, oop, there we go, 25 minus, here we go, 0.11 H. And then similarly, we are in Erie gaining 11% of the current levels of H, and we're losing 36% of itself. Similarly, Ontario. This is for early differential equation students. This is a challenge because they want to do exactly what Andrew, I think you were sort of getting at, was trying to find an equation for H. And we want to talk about just the change. The explicit forms, we do need some techniques. All right. We can also use a recursive system. And this is a nice way to present Euler's method. If you're in a single variable calculus class, where their equations look like this, where we have after one iteration, or each iteration, you are adding 25 and you are losing 11% of what is already in there. So it's a whole minus 0.11, which gives us the 0.89. And then the others follow. In terms of how much you would guide students through this, I really like to take like a hands-off approach, especially since with modeling, you want them to get messy and dirty and in it. But it does depend on how much time you have to devote to it in your curriculum. So you could speed things up by kind of guiding them towards this, or at least giving them the first one or talking it through and letting them develop the other two. So I also like to give students an opportunity to gain skills in spreadsheets if they haven't done that before. So I do have them set up essentially Euler's method here in Google Sheets, but you could do this in Excel, any other spreadsheet. The nice thing about this is that you can find values that you are interested in. Can you still see my screen? Good. Okay. I was concerned because I was switching back and forth. And it allows students, again, to kind of dig in. And sometimes what I do is I present a template, like do an example that's out of context and provide the template, and then they can develop their own spreadsheet from scratch. Another thing I like to do with Google Sheets is I give each student a tab and I lock all the other students. I only give permission to the student for whom that is their tab. And then they can work in it. And then I can view tab to tab. I can watch them working, which is a really nice, if it's a Google campus, then that really works well for you. Oh, no, there we go. All right. Yes. So if we look over the next 5 years, we see sort of a trend. And try to, and I like students to kind of dig in to see if they can analyze, get anything out of this in context. Remembering that Huron, that's the tons of pollutant in Lake Huron in that specific year after measurement. Here I use Desmos for the recursive system, and I see I get these trends, which is also a really nice opportunity to analyze what we see, use vocabulary that they're building. Again, you can either give that to them or have them develop that in Desmos. And then as we saw in the spreadsheet, I'm going to quickly pop out of this. An interesting question may be, how many years will it take for the levels of pollutants of each of the 3 lakes to be reduced to 10% of their present values? So for Huron, that would be 350 tons. So then they could pop over to their, there we go, their Google Sheet, and then we can see Huron is column C, and we see that it must happen somewhere between the 28th and 29th year. Excuse me. And then we do the same with Erie. 1800 was the initial, so 180 is what we're looking for. And then for Ontario, it was 2400. So we look between 57, 58 years. This again gives them a very accessible way to interpret what we're looking at. and make meaningful conclusions. All right, so let's go back to the slideshow. All right. If we're thinking equilibrium in Lake Huron, long term, does the pollution level ever stabilize? Or do we continue accruing? Again, this is something that I don't like to guide students towards. I kind of just present the question and say, how long, or excuse me, how many tons, if at all, do we reach in the long term? So suppose I gave this to students and I asked, why is this correct? As opposed to just letting hands off and letting them come up with it. If I asked a student, wanted to guide them a little bit, why would we say H equals 0.89 H plus 25? What does that mean? Why would that help me find the equilibrium?
Well, you can solve for it. It's a linear equation.
Well, but also when you really are going back to the derivative, right? I mean, it's like you're
Yeah.
saying your change in H is equal to 0. So you're just saying equal to 0, that's what equilibrium means. And that, yeah.
Exactly. Exactly. Yeah. And Paul, you said it too. I'm getting the direct message. Exactly. Yeah. Equilibrium occurs when DHGT is 0. And that allows us to then solve explicitly for H. Yes, Scott. So I see what pollutants remain and what is being pumped into the lake. If we look back at the spreadsheet, our algebraic equation provided us with a value that is exactly where we see the trend going, 227 or so. Let's go back here. All right, well, that was easy. How about, let's try with Erie. Let's see what happens there. So here, we're sort of using an assumption that Lake Erie will reach its equilibrium when Huron reaches its equilibrium, which intuitively makes sense. But again, that's not something I would necessarily tell students. I would have them come up with this kind of thing. Okay, so we do our algebra. We get 69.44. And if we think back to our spreadsheet, that's exactly what we saw in the long term. And similarly with Ontario. And I'll go back to, there we go, spreadsheet. Yep, so we have 69.44 and then 208.33, confirmed. Okay. I hope I'm not making anyone dizzy with this hopping back and forth. So please let me know if I am. All right. So here's the scenario again. What if we went the route of differential equations and solved those explicitly for explicit forms, or excuse me, solved for it analytically using getting to explicit forms? Same scenario. We look back at our differential equations. How can I get an explicit form for H as a function of time in years?
The integrating factor method should work.
Yes, is there something even a little more, even a little bit simpler? Or earlier in the diffie-Q
Separation.
content? Yeah, separation of variables. Yeah, absolutely. So again, this will be something certainly after you you have worked with a number of techniques. If it was a differential equations class. So yes, the first one we can use separation of variables quite simply. Here we are. And then given our initial condition, we can solve for our constants. Okay. And are we surprised that we have a negative exponent here? And is there a significance to this 227.27? It's a familiar value, right? Nice. So I see Scott. Yeah, I'm reading Scott's chat. Yep. Yep, exactly, Paul. Steady state value. Okay. Now with DEDT, can I use separation there? So I have my H now. I'm going to substitute that in here, but that still leaves me with a differential equation that involves the sum of something involving E itself and this exponential function. So at the last line there, am I able to use separation of variables there? No.
No.
So here, Tova, you're exactly right. Integrating factors would be a really, really useful approach. So I know in our single variable calculus class, we don't present this as one of the techniques. So we essentially teach it to them in service to this. It is not part of our calculus curriculum, but it is part of our differential equations curriculum. All right, so we can now solve for E and we get this explicit form. We could do the same with Ontario. And I'm happy to provide full solutions to this, I think it's Lee Noble, who's going to be taking care of the handouts and things. So yeah, if we look back at our Desmos graph, the dots were our numerical approximations, the Euler's method, and the functions we just got, explicit forms, are now graphed against it. They're good, quite good. Now, it's enough to get these, well, it's enough for now to have these explicit forms. But as with anything in our mathematics classes, we really want, what the meat of it for us is the interpretation, the analysis, and comparing, contrasting. So what is the benefit of having a closed form equation, giving us several advantages over the differential equations? We can, and these kinds of things, I may have students generate it. But in the interest of time, I want to make sure we get through this. So, but again, this kind of thing I would have students generate. I wouldn't just give it, because I believe that's sort of passive learning as opposed to active. So yeah, we can see immediately that the long-term pollutants levels in the 3 lakes are those 3 values you see respectively. If we wanted to note the amount of pollution in Lake Huron after 12.5 years, we could just evaluate the function. If we want to know when the level is in Lake Erie will be below 500 tons, we could solve numerically. We could also see that the level of pollutants in Erie and Huron always decreases, while the level of pollutant in Lake Ontario increases before it decreases to its steady state. Nice. Yeah. So these I list on my syllabus at the very beginning of the course, and it's available to students all throughout the semester. But I think it's kind of nice. I know I like to revisit them as I'm teaching the course and ensuring that I'm actually hitting all of these. And I think this problem does so much to address the learning outcomes. So yeah, setting up and solving simple equations using standard techniques from calculus, like separation of variables. Students will be able to use these techniques to write and solve equations to models, classicals that model classical situations from physics and other applications. Recognize when an equation is not solvable by those standard techniques, and be able to implement numerical methods using technology to approximate solutions. I think it's something, especially this third point, solving modeling problems, particularly open-ended ones, especially for students who have not had a lot of experience in that. It is really hard to adapt at the very beginning because there's so much uncertainty and there's so much like open to interpretation and open to justification. And just like Scott and Ben, you were saying, well, I think this method would have been actually more powerful than another. So it just generates really good conversation. Yeah, and then one of my highest priorities with every student that I teach is to give them opportunities to communicate their understanding, both verbally and in written word, not just listen to me kind of passively. And then some others, again, these are all listed on the syllabus. I don't include these in my, like in the actual write-up of this problem. It's something I may remind students that I really value. demonstrating correct mathematical notation and technology when writing, using collaboration to solve problems, just as we did, writing mathematical functions and differential equations to model situations described verbally or graphically, and then using technology when appropriate. Like we saw spreadsheets and we saw Desmos. In another talk that I did earlier, we needed eigenvalues and eigenvectors, so I used Wolfram Alpha. But it's so nice to give students these different tools, and then they have to decide when to use them.